the main point I want to get across is don't put something on a print unless you have some basic idea of how it's going to be inspected too. Who is this print for? Why did we make this thing? Most people would say, oh, it's for production. They're going to try to make it, right? Actually, when you're designing a production print, it's made for inspection. Production doesn't necessarily, and this is, I take this with, doesn't necessarily care about what tolerance you put on the print as long as they can hold it. For them, it's really a binary thing. It's, did I hit it or did I not hit it? And if it's really tight, they're going to say, I can't hit that, or I'm going to have a tough time hitting that all the time. But really, it's a did I or didn't I do it? But this drawing is really the manufacturing limits for inspection. This is an inspection print. When you're designing a part and putting all your tolerances on it, it is for inspection, whether it's the machinist doing the inspection or whether it's an inspector doing the inspection themselves. This part, how my datum structure is set up, will determine how I set the part up on my CMM if I'm an inspector. I have to follow the guidelines and the rules that you have laid out. Machining is just going to shoot for the perfect CAD model that you make every time. In fact, you can just send them the CAD model, and they're going to make it as good as they can make it with the processes they have. Yes, if they see a tight tolerance, they may adjust their processes, especially if they're design responsible or a supplier. But they are pretty much always going to say, hey, can I hit that realistically? Yeah, my machine can hit a 1,000th of position tolerance every time. You've got 2,000ths. I'm perfect. Inspectors, though, have to follow the rigorous rules that you put on your prints. What is the datum setup? How do I set this up for inspection? How do I create my inspection plan based on what you put? This is an example inspection plan, by the way. This is something that many of you may have seen as well. This is called a bubble print. This is what an inspector is going to do with your print. They're going to go into it and they are going to bubble it up. And this, each number here is a number they have to report to you or report to production on the inspection report. And if one of these numbers is off, they have to red tag the parts and could put in a deviation, and basically they can't use the part. Everything has to be met. Someone says, well, which dimensions on this print are important? Which ones do we have to meet all the time? The answer is all of them. There's no, the way you determine what's more important than another thing is how tight that tolerance is. So you have to understand or have a vague idea. You don't have to understand how to operate a CMM or do a height gauge measurement or anything like that, but you should be aware of what the inspector is going to do or how this part needs to be inspected, or even just how much inspection needs to be involved in this part. Here's one version of the print that I have, and here's a separate version that I designed after communicating with my manufacturing engineer and inspector, which allowed us to be able to build and design a gauge right on the line so that we didn't have to eat up CMM time, and now they can pop it right in the gauge, and it verifies all these red things right here. All of those are specified right away with my gauge that I have, this air gauge. I can't go into how the design is of it, but this is designed for manufacturability right here, designed for inspection. I'm working with my manufacturing department to reconfigure something still functional, but making it so that they now have the ability of using a line side gauge and don't have to take up an hour of CMM time, depending on how big the part is. So that's where I'm going to end right here. I'm going to start getting into Q&A. I just wanted to say before I get into Q&A, there should be a handout available to your group. If there's not, I can paste this in the chat. If you want a free GD&T wall chart, we've got this beautifully designed wall chart that we give out for free showing our framework that I talked about today. Size, location, orientation, form. It includes all 14 of the core GD&T symbols, which, by the way, there's 12 now. They got rid of concentricity and symmetry in the most recent standard. Doesn't mean they don't exist, because about 85% of people are still on the 2009 standard. So, but anyway, it includes all 14 symbols that are available, and is a great little wall chart or guide if you're inspecting, if you're designing, if you're doing anything and trying to get into GD&T. So I hope you download it. I hope you like it. I hope you enjoy it. We also include, we have a newsletter where we don't sell you anything. We just have some cool things from around the industry, typically something educational, something interesting, something funny that we send out once a week. So we hope you join us on our list. We'd love to hear your feedback too. So now I'm going to get into some questions here. These are actually going to be maybe in reverse order. I'm not sure. So I will start here with machinery handbook recommendation. I would just get the most up-to-date version. Each year there's a new version. Just type in machinery handbook to Amazon. I think there's only one brand out there. There might be multiple, but honestly, if there is more than one brand that I'm not aware of, all the tables are just taken from engineering concepts from back when my dad was a baby. So it really doesn't matter. You know, there's really not much updating that they do. They reorganize it. They might add some new stuff, but get whatever version is cheapest. If you want to get last year's version, you're not going to miss out on much. Not much has changed in physics and engineering since then. So yep, I'm going to do that. Can you explain? So let me, that answered that one. My machine is, again, search for Amazon. It's just called the Machinery's Handbook. I'm trying to remember the publisher, and it's killing me right now because it's on my desk downstairs and I don't want to leave this webinar. I could go grab it. Can you explain how MMC would apply to clevis holes? I don't have time to explain to MMC all over right now, but I can give you the gist of it. And what MMC is MMC is a modifier. It looks, let me actually pull this up. Go back to the print because I do have it for the, I don't have it on that clevis hole. Do I have it on this one? Okay, let's not use that one. Let's do this. This little M symbol here, and I'll zoom in on this. This is the bolt holes for the assembly, but this little M symbol here, everyone, it's a very common question that we get. Real quick, we do have a video on YouTube that goes into this in length. I would just Google GD&T maximum material condition. Look for the GD&T basics video. It'll probably be one of the first ones that you see where we cover it. However, just kind of the 2-minute overview. What this means is we are actually giving a variable tolerance to production. So what I'm saying is when I'm giving a position tolerance, I'm giving you 12 thou here at MMC. The MMC for a hole is the smallest size hole. So when this hole comes in at the smallest, I can be 12 thousandths off the perfect center. But as this hole gets bigger, I can be actually further from the center now. I get what's called bonus tolerance, if you've ever heard that. It's a variable tolerance that says at a minimum, I get 12 of position here. But as I move away from MMC, the MMC size, I actually get more tolerance. And that makes it way easier to produce because as I'm kind of, working with a part and drilling it, my hole's going to get smaller as my tool wears. Well, now I get less position and now I know when to change out that tool if I'm a manufacturer. It also allows me to make the hole bigger because if the hole's bigger, it can be further out of position and still assemble with the bolt that goes through it. So that's really the concept behind it, is because as this hole gets bigger, it'll still directly assemble when it's out of position further. We're giving that variable tolerance for things. So that's kind of the high level overview of that. What extent should tolerances account for gauge measurement variation, meaning a gauge has a gauge R&R of 20%? Should the tolerance be tighter or allow for this measurement error? Let me see. I'm not sure why I can't hit answer here, but I'll just answer this one. Usually we recommend 10% of the tolerance. So the gauge should have 10% or less of the tolerances it's inspecting. So for example, again, on this, this hole right here, if I had a go, no-go gauge, well, there's 7 thou of tolerance here. We'd recommend 7/10 or less on designing the gauge for the tolerance of that diameter. That's just a rule of thumb. There are entire standards. The Y 14.43 gives a lot of the gauge tolerances. That's the ASME. Y 14.43 gives a lot of some specific gauging rules, especially for functional gauging. But 10% is like the rule of thumb if you're designing gauging. So what's your position on reference specs listed in the drawing, meaning they're critical dimensions that are listed, which are inspected, part of incoming and component inspection, Non-critical dimensions may be listed as the supplier making the part. There are reference specs, which are desired features and not be measured. A chamfer on a hole, reference spec of that. Reference dimensions are typically ones that, a good example of a reference dimension. I'm not sure if I have one on this print here. Let me see if I zoom out. I don't think I do, but a good example of a reference dimension would be, let's say you've dimensioned one feature here and one feature here, but then maybe the total length. Well, to avoid double tolerance stack up, you'd give it a reference dimension, just because they might do, and we call them sanity checks, where they take just a set of calipers and check it and like, the overall size of the part for the machinist is good. I can send this to quality knowing I didn't really make it screwed up. That being said, critical dimensions, that is a quality term. That is not a design term. Every dimension that you put on a print is the limit that you can physically allow as a designer. So it has to be met. You can see down here, and I'll zoom in, that I have this catch-all thing, and this is a good thing to put on prints. All surfaces all surfaces profile of 30 thousandths to ABC. There's some features on here that I didn't actually dimension because I know that they're just sitting in free space, right? Now, if the part was dropped and I had a physical, if I could see that it was dented, well, I may reject the part and say, hey, it's not met based on that. And in fact, if we go here to my my inspection plan, you can see that there's different reporting frequencies that I have in my inspection plan. So critical dimensions are not necessarily for design, they're more for quality. Everything has to be met on a print every time. It shouldn't be on the print if it's not, right? And it shouldn't be a limit. If it can be met and you're just putting it on there to guess, open up the tolerance and then we don't have this problem. But the frequency or the inspection plan or how often you check it or verify it, right? That can change based on these critical dimensions. The automotive world, I worked at ZF Transmissions and I also worked on the park lock system. The park lock system is a very critical safety system, as you can imagine, in a car. So any sort of variance or any sort of tiny error or something like that had to be almost 100% inspected for any sort of, variation that they found in the machining and manufacturing process. They had line side gauges to check a lot of that and things like that. Yes, that is a critical dimension, but as a designer, I'm giving you a tight tolerance there because I know it has to be within that limit. As a quality and production department, it's up to them then to determine how often do I have to inspect that. And usually these critical dimensions that you see on prints are the feedback from the quality and the manufacturing department of what do we see as important. But when you're a designer, you shouldn't put something on a print that they can't hold or that you're hoping for the best. If it really can be open, make it open. Otherwise, make it a wide open tolerance. If it can't be, make it tight. So that's really a quality thing, but that is a very good question because honestly, you have non-critical dimensions and you can see down here in my inspection plan, I have this EE and there's a couple, this is the first page of this, but we do have a couple dimensions on there. The EE is only if a defect is found. I mean, if I pick up the part and I can't put the screw in, well, now I go and inspect it. Maybe I have a supplied part or something and it doesn't assemble. Well, at that point, now I do my inspection, but it's not a part of my inspection plan. So it's really a quality term. And don't get me wrong, design can be absolutely involved in those decisions. But when it comes to a designer's main role, it's to preserve function. Everything on your print is the functional limit that you can allow. Moving forward, what is your position use on the typical call out? Does it apply to the sheet? Is used anywhere in multi-component design package? Let me go back up. What is your position in use of the typical call on the multi? So these are both the same question. So let me go back to the drawing and let me take a look here. I don't see my typical call. Maybe it was on a different print. Let me make sure. TYP is really being replaced or enforced in the standard of being the 4X or the 2X. Really, you're not supposed to be using TYP anymore. Let me get the printout. What you're supposed to be using is the instances of features that you have. So the 2x, I know there's 2 clevis holes here based on the geometry of the part. So that's clearly defined as being to that 2x. You try not to use TYP anymore because it can lead to confusion. Maybe there's a 3rd hole here that I had and I was just looking at the part too quick. And if I didn't put the 2x or the 3x or whatever, I would be missing something. So that's why the 2x is now, I think in the 2018 standard, they got rid of TYP altogether. It's still kind of going to be seen on drawings. But the question is, what is your position on the use of TYP callout? Does it apply only to the sheet, or is it used anywhere in a multi-component drawing? I would try to, the problem is sometimes dealing with like, let's talk about like a casting drawing, a transmission casting. That's a 17-page drawing. So if you're going to be using, you know, typical or 4X or something like that, and it's on some random obscure page, you know, I would say as your package grows, especially if you're dealing with assembly or something like that, notes are your friend there. Make it easy to understand. Be very clear. Or maybe, you know, if I couldn't see all 4 holes on this call out here, maybe I'd get a view where I can, or like a detail view where I actually just isolate those 4 holes and then I give it 4X and that. Again, communication and clarity is the goal of drawings. That's the #1 goal. And I always say, you know, don't try to invent something that doesn't exist. Don't try to, you know, use extra GD&T symbols or something like that. If it's just a quick, you know, 4 holes, you know, little note right here. Maybe there's 2 layers of this, only applies to far side holes or something like that. If it's unclear. So that's how you can do it. So yeah, so let's see. I'm trying to see if I missed anything. Let me go back up to the top here. So do assemblies use tolerance charts, or is it just dimensions? Assemblies absolutely can use tolerances. They just typically have a lot fewer. Because if you think about an assembly is really just a part made of parts. So if you've already met the requirements on these subcomponents, you don't need to detail it again. And that actually goes back to that reference dimension that we talked about before. That's another very common use of reference dimensions, is it's on the assembly print. Well, you have it as a reference dimension because we don't check it at this stage. We check it at the earlier stage. So, you know, if we have a gear that goes into a bearing and now it's this assembly that's on a shaft or something, we're not going to be checking the gear's run out to the ID of the gear, right? But we may be checking the gear's run out or the outer, you know, teeth or the tip diameter relative to now the shaft. So we may have something, but now whenever you get to an assembly drawing, just view it as one part again, but don't duplicate work. Don't repeat dimensions that now have to be further inspected if you've already inspected it and there's no physical way that it can be changed. One other component with that is like heat treat. So for example, if I have an inspection before heat treatment and then I have an inspection after heat treat, well, that's going to change, right? We know with heat treatment, things get wonky and wobbly and all sorts of things. That absolutely can be inspected at both times. But if I have this, let's say, for example, I have this thing right here that I'm measuring, and now I go ahead and assemble it, and something's like mating with it, there's no reason I have to inspect it again. The geometry of that component hasn't changed. So just use best judgment when it comes to that. But absolutely, assemblies can have tolerances and should, if they are not on the subcomponents themselves. Okay, that was good. I'm in a little 2 minutes over, so I hope that you all enjoyed that. Again, feel free to jump in, download your GD&T chart. We'd love to have you on the website too. We're also the biggest source of free GD&T information online. So visit us at gdntbasics.com. And we hope to see you there. And thanks for joining me today on this session.